10,000? No, this is impossible.
All right, my friend. Recently, I made a stupid, silly survey, and it seems like 50% of you would like to see bigger projects in C, and 44% would like to see them in an explain me like I'm 5 way. Surprisingly enough, nobody have chosen this option, which was my favorite. Anyway, so today, my friend, we are doing the push swap project. If you don't know what I'm talking about, you just come here on Medium. As you can see, push swap the least amount of moves with 2 stacks. You can find everything explained here. And nonetheless, I'm going to explain you as well what is this push swap algorithm. So we start. I prepared this little presentation so we can understand very well what is going on, because first of all, we have to understand what we have to do. What is the task on end? So basically, we have a series of numbers as an input, and we have to sort all these numbers in ascending order thanks to specific commands. So the commands are the constraint. For now, focus your attention only on the syntax. You see, I launch the program, push swap, and as an input, I have 3 arguments coming from the command line. Then this input gets processed by the push swap magic algorithm, and then as an output, I get these lines. As you can see, I have RA and SA. These are the commands that I can use in my algorithm. Essentially, this means rotate the stack A and swap the stack A. By now, it doesn't mean anything to you, but no worries. So at the end of the day, you have to implement an algorithm. An algorithm is just a fancy way to say a series of instructions that perform a specific task on end. So you can say everything is an algorithm. Watching this video is an algorithm. You opened your computer, you turned on the Wi-Fi, and you logged into my account, and now you see this video. That was an algorithm. So you can consider this video like a mini course on data structures and algorithms. I will explain to you these ideas in the practice itself, because I think that when we explain abstract ideas, not really linked to reality itself, it's super difficult to understand. So first of all, my friend, I want to show you all the project in all its glory. So as you can see, this is composed of many files. Basically, a project is just a directory. You have a directory with many files. Here we have the GUI view, which is the one we use. And here we have the terminal view. We have a bunch of C files. We have also an header file, as you can see from the extension here, H. And this is very useful when we deal with projects. I won't explain to you what is an header file and why it is important with multi-file projects, because this is another argument. This is another idea. And you have to understand compilation, why we need object files, and so forth. Maybe I will do that in another video. By now, we are just going to focus on the problem on end. Otherwise, the video is going to be dramatically long. So long story short, another file is just a file that contains all the necessary prototypes, basically all the functions that I need to be visible to all the files. For example, here I have some functions to create the stack, some function to handle errors, and a blueprint to create a node of the stack. I include also some header files, for example, the UniSTD, Unix standard to use the write function, and so forth. And here at the bottom, you can see I have all the commands that I can use in my projects. That's all you need to understand by now from the header file. So you know perfectly well that every C program starts with the main function, right? The queen function of all the program. So this is the access point. When the process is going to be launched, this is the first line of the entire program. You should be able to understand all the program only by the main function. If you read the main function and you have a rough understanding of what is going on with all the project, well, this is a good main function. This is a good modular project, okay? Because it is basically a resume. You can understand the main function like a little resume is going to call all the functions which are needed to perform the algorithm, the task on end, to sort a series of nodes. As you can see here, I declare 2 pointers to stacks, and initially they're set it to null. It is always good practice to initialize a pointer to null to avoid some segmentation faults, because we cannot dereference null pointers. Then here some controls, another control, and then here a function which is stack init. You can understand that probably this function is to create the stack, right? You're gonna create from 0 the stack. In this case, I give the address of A. Basically, I give the address to the first node. So if we watch carefully this main, I have a check phase right? Here I have a check. Here I have the creation of my stack, and here I have the algorithm itself. I'm saying if the stack is not sorted, basically if the stack is not in ascending order, you do this or you do this or you do that. So these are the algorithms, and this is the free. So basically clean it up. So you can already see, roughly speaking, what is going on. I have a first part, check if the input is correct. Second part, create the stack. Third part, the algorithm. Of course, you shouldn't understand nothing by now, but this will be useful later. So my friend, I'm gonna show you first of all a little tester that I found online to prove if the algorithm is working. First of all, I'm gonna do 100 numbers, 50 tests, and let's launch it. Basically, this is gonna test in how many steps my algorithm manages to find the correct solution. Of course, I will leave you a link in the description for this tester. Okay, it seems like everything is correct. So maximum instruction is 665, 543. Average instructions is 606. It means that to sort 100 numbers with only the commands that I can use, I need all these instructions on average, right? With this algorithm, 606. Now let's try with 500 numbers. So to me, the most important thing is the leaks, because I always have this box, which are... Oh, my friend. Okay, so for 500 numbers, I have on average 5,510 instructions. Basically, it works. That's the main point. So we're gonna just do some practice with the code. As you can see, I can launch push swap with some random values, for example, 2, 1, and 34. And I get as an output SA, that stands for swap. I can also call this algorithm with many numbers. For example, let me call this with many values. For example, -42. As you can see, I get a longer list of commands. Pay attention that I can give as an input also a quoted series of numbers like that. It is exactly the same, but for the command line, it is not the same. These are two arguments, while here I have many arguments, okay? I explained this idea in a previous video. If you are like, what the heck is going on now, you can watch the video and hopefully you understand very well what is going on. So the algorithm is not going to work if you have an error. For example, you write a number like that, or you write something which is not a number, and so forth. Basically, this is the control phase. Okay, let's understand better what is going on. So first of all, what is a stack? What are we talking about? Well, very simply, a stack is like a pile of plates, okay? You have a series of elements which are stacked one over each other. And you have a top of the stack, which is the top plate. You can put stuff inside the stack with an operation which is called push, okay? So when you push an element into the stack, you're gonna put a plate at the top of the stack. Your operation is the pop operation, basically when you remove the top plate. Okay, now the top is pointing one plate less because you have removed the top plate. Fairly simple, right? The stack is this data structure. Hopefully you know very well what it is, because you have a stack while you're launching a process, right? You have in the process memory area, you have the stack date, right? You should know to make this project this very basic concept. So we have to implement in our algorithm a stack. Personally, I have decided to use the linked list. A linked list is a very flexible data structure composed of many nodes that, in my opinion, is the best for this kind of problems. You can also implement a stack with a simple array, right? You just pretend that every plate is like a slot in memory, and that's it. So if you have 30 numbers, you have an array of 30 integers. That can be a stack as well. But in my opinion, and you will see very soon, with an array is not so easy to implement the commands that we will have to use and implement. Anyway, with all the data structure, there is a trade-off, which is how much space in memory is going to occupy this data structure, how easy it is to manipulate the structure, how fast you can access elements in the structure, and so forth. So every data structure has its own plus and minuses. This is very easy to manipulate. You will see that it's very easy to implement the swap operation, for example, which is like the swapping of the first and the second node. On the contrary, it's very easy to perform a segmentation fault and get confused with all these pointers, because every node of this data structure as the next pointer, namely the one which is pointing on the next node and the previous node. So when we have to change these pointers, maybe tricky, but you can change this stuff. You can become fairly good on that. So I think this slide is fairly powerful because, as you can see, I take every argument which is in my command line, push swap and all the numbers, and basically I take every of these strings and put inside a node. So the first number in this argument is the top node, while -16 in this case is the bottom node. So it's like 1337 is the top plate of my stack. Do you see that? That's the idea. Now, my friend, if you struggle with linked list, you can watch this playlist from Code Vault. This page is marvelous. I suggest all the time. So yeah, you can understand very well what is going on. Now, coming back to us, let's understand very well what is a node. What is a node, how it's made. So a node is a struct. A struct in C is like a container that contains some data. You can perceive a struct essentially like an array. The big difference with array is that inside a struct, you can put different elements. Namely, you can put elements which have a different size. Contrary, inside an array, you can put only integers, for example, only charts. You cannot have an array with different elements inside. If you dereference an array and you have different elements, it won't work because you cannot do pointer arithmetic, and you know very well that an array at the end of the day is going to decay into a pointer to the first element. So the array data structure won't work with elements which are different in size. On the contrary, a struct is fairly flexible. You can put everything whichever you want. The classical example is like a struct person which has a name, which has an age, which has a work, which has a wage, and so forth. You can put all these data, and it's fairly cool because it's gonna contain related data into a single element. It's fairly useful. So I exploit the power of structs for my project. As you can see, the struct, of course, contains the value, which is the number. In the first case, I have 1337. Then I have the current position, which is a metadata, which is going to be useful for the algorithm itself, so you can forget by now. And then very important, every node has a pointer to the previous node and to the next node. This allows to create a linked list, basically a series of nodes chained one each other inside the heap. So very interesting, but what is in practice a node? How to implement a node? Well, we have to go in our push-swap.h. It is on the push-swap.h because I want to use this code in all my files. So including this push-swap.h in every file in my project, I can use this specific data structure. So let's watch very briefly the code. So this is a struct, my friend. This is a struct. This is a blueprint of a struct. Okay, you can forget by now by this the typedef and typestack node, which is just auxiliary stuff to make stuff easier. But a struct you essentially just need this keyword and the name of the struct. Then, as you can see, I have the container here, which is surrounded by curly braces. It's fairly easy, right, to see. You have this container. Inside, I can put all this data that I'm gonna need. So you can just perceive like a block filled with this data. I have the value that you saw, the current position, the final index, the push price, above median, which is a Boolean, cheapest. Of course, this is data that you should not understand by now what it means, but just keep in mind that just to show you how to build a blueprint. The important ones by now are these: the pointer to the next node and the pointer to the previous node. These are fairly important. These are the pointers that allow me to create this linked list. Very elegant data structure. This is another pointer for the algorithm itself. This typedef and this one is just to say, hey, from now on, when I want to use this node, I won't type struct as stack node. I'm just gonna type stack node. Hopefully you know what this typedef is. If not, just ask ChatGPT. Is fairly simple. I won't waste time with that. The only thing that you have to know, in my opinion, here is that while here you have still to use the full struct as stack name node pointer to declare a pointer to the target node in this case, and why you cannot just use this type stack node pointer. Well, because first of all, you're gonna perform this code. Okay, you have this Then you have the declaration of all the variables, and only at the end you have this typedef. You have typedef and t stack node. Basically, only when all this code is going to be performed, you get, okay, from now on, you just call all of this chunk of stuff type stack node, okay? Thanks to this typedef. So at this level, when we have this declaration, this type stack node symbol doesn't exist, okay? This was a thing that I didn't understand, but hopefully now I do. So this, my friend, is a node. This is a carrier of information that I will exploit in my algorithm. This is the code itself, and this is the visual part. Fairly simple, right? You can really depict in your mind a node as a cube that contains a lot of stuff. Now, what I have to do. Let's go back to the main function, right? The first function, and let's just follow the program itself, like the compiler would do. So we go to the main, and here you see immediately that I declare a pointer to a node, right? That I call A. So now you understand that this is a pointer to a cube, to a node of this stack. Initially, as I told you before, we have a null pointer. This pointer is pointing nowhere. So we cannot do any kind of damage, any kind of segmentation fault. Then initially I do my checks, all right? If I have to check if the argument counter is equal to 1. In that case, there is no input. Argument counter equal 1, it means that I have only push, swap, and anything else. Or here I say if true is equal to argument counter, namely, yes, I have 2 inputs, but the first char of the input is 0 immediately, \0. It means that it is a string. It means that this is an empty string, so you can just finish here and we are done. So basically, this case is here. When I have nothing here, you see, this case, I just return. And as you can see, the return value is 1. Or when I have an empty string, like that. These are the cases handled by this code, okay? Easy. Here I just type in this fashion, because very often I have a bug in which I reverse the two and I only write one single equal. And this is an assignment, and this is okay for the compiler. This is not a mistake. This is just a trick to be sure that I don't perform an assignment here and there. Now, let's go here. If the arguments are indeed true and the string, of course, is not empty, what do we have to do? We're going to assign to argument vector, which by now I hope you know what it is, thanks to the video or resources that you stumble online. We assign another to the array that we are going to create with the function ftsplit. Then now we are going to see. We're going to give as an input argv in position 1, namely we are going to give the full string with all the numbers, and a separator. In this case is the space. I have written literally the space. I could have written here 32, which is the ASCII value of the space. It is the same. Now, where is the split function? Well, the split function, my friend, is in a file by itself, because it is a longish function, as you can see. It is as well composed by other functions. Specifically, it is composed of 3 functions, right? It is a longish function. So as you can see in my main, I have the call to the split. So in one line, you have collapsed a lot of complexity, a lot of lines, specifically 112 lines. Okay, it is going to be less because I have a lot of comments here to make it simple to understand what is going on. So to make it simple, what is going on? If I have an input like that, or if I have an input like that, the function has to behave in the same manner. But you know very well that, I repeat to you, this is just 2 arguments, while here I have 4 arguments. And the argument vector here is totally different. Here I have an argument vector with only 2 elements. I have 2 strings, while here I have 4 strings. So I work out this deal with the split function, okay? So to understand this function, we have 2 approaches, basically. Explain line by line what is going on and start to cry and scream. Or the one I prefer is to have a visual understanding of what is going on. Basically, I'm going to exploit the ctutor. Okay, ctutor, in case you don't know, is just a very friendly tool for debugging, because you can see visually, you can appreciate what is going on with your code. So let's very briefly watch what I've written. So here, as you can see, I have my main with argument counter and argument vector. At argument vector, I'm gonna put the result of the split function, the one I'm using, right? As an input, I'm gonna give the string literal hello there with a separator, which is 32, which is the space. We are gonna see visually what is going on with this split function. So we start from the main, and immediately we jump into the split function. Pay attention to here. As you can see, I have the main function in the stack, and then I have the heap. The split is working indeed in the heap because I'm going to use the malloc. So next, now we are inside the split. As you can see here, I have the function scope, which is just above it, the stack. Indeed, we are working with stack even in the process world. So here I have a value, which is words number. Here I declare star vector strings. If you have any issues on reading variables in C, I show you this trick. This is called the right left rule. And this is a way to read complicated elements in C. It's fairly simple, my friend. First of all, you find the identifier. Then you look at the symbols on the right, and then you look at the symbols on the left. Let's try an example very fast. I will link this stuff in the description so you can dig it down as you want. Here, what do we have? I have P, which is the identifier, which is, as you can see here, an array of what? Of pointers to int. P is an array of pointers to int. P is an array of pointer to int from the right to left. And here it's just going on, and you have very strange declarations which will become easy vanilla to you to understand. Another cool trick is this one called the spiral rule, I guess, as well. I leave the link in the description. We should not waste time here. Okay, basically we are here. I'm going to declare this vector strings, which is a pointer. Here I cannot go on the right, so I have to go to the left. A pointer to what? To a pointer to a char. Basically, this is an artificial argv. Here, as you can see, I have a pointer to the string literal hello there, which is not in the heap, but it is in a read-only storage. I made a video about this idea of strings which are only read-only spaces. Maybe just check it out. But keep in mind that this is not the heap, so we don't have to free this stuff. Okay, so what do we do? First of all, I have to count the number of words which are inside the string. Hello there. I'm going to do that thanks to this function, count words, that takes as an input the string and the separator, which is a space. This function basically is going to tell me, hey, given that specific separator, tell me how many strings are there. Here we can see immediately that we have 2 strings, right? Because we have 1 separator and all these chars. So let's watch these count words, how it works. So we are here, and then we jump into the function. As you can see, I have another function which is called in my stack calls. So here I use a Boolean variable, which is inside word. Basically, this is telling me, hey, now I am inside a word or I am not. And then, of course, I have the variable count, which is the standard variable counter. We start, of course, from 0. Let's go on. Of course, the count words as a pointer to this literal string. And then we start to iterate inside the string, searching for the number of words. So I say while str. I hope you know that this is like while str is different from 0. It is exactly the same. Here I just exploit the value pointed by the pointer str as a Boolean value. 0 is false. So when we reach the final \0, it's like false in this moment. So we keep going on. I assume initially that I'm not inside a world, so I say inside word equal false. And I say while at str is equal to separator, you just keep going on. As long as you have a space, you just go. You just iterate inside the string. So initially, at str is equal to separator is false because I'm pointing to the h. So what do? We just keep this while, okay? And we go while at str is different from separator and str. So basically here there is written while I have a char which is different from the separator, the space, and we are inside the string. Basically, we have not crossed the \0, the sentinel terminating value for the strings. What do? We go inside this block and we say, this is a very important if, because I say if not inside word. Basically, if we were outside the word, it means that now we have entered inside the word. So what do? I just increase the count, as you can see, plus count. So 1 word, I said 1 word, and I say inside word equal true. Now I am inside the word, okay? And I keep increasing the string. I'm doing pointer arithmetic here, plus str. I keep going on. While at str is different from separator, the same thing. I am here at the e, then I go inside. And as you can see, now I don't enter anymore this if. I don't increase anymore the count because now I am inside the word. So what I'm going to do, I'm just going to increase this until I have a char which is not like the separator. At a certain point, I stumble upon the separator. You see? String is equal to separator, so I'm going to exit this while. I go out. While at str, this is still a char. So what do? Next, inside word equal false. So we flip again the Boolean value. So I am outside the word. Next, until I am inside the separator, you just keep going on. And now it happens that I have only one, but I could have like 1,000 spaces. It is totally the same. And then we keep going on, okay? And then we repeat. Basically, the trick here, what is? When we jump from outside to inside, I increase by 1 the numbers of words. So I think you have a clear view of what is going on, right? It's not terribly difficult. Just try to understand by yourself. Visually, it's super simple, in my opinion. Okay, long story short, I'm going to count all the words, and then the function is going to return, as you can see, true, the number of words that I have. Cool. Words numbers equal true. So now we are back to the split. What we do with this words number? Where we're going to allocate space in the heap. I'm going to malloc size of char star, namely size of a pointer, which is 8 bytes, per words number, which is equal to true, because I have a lot there, plus true. Why plus true? Well, because I want to mimic the argument vector. And as you know, the argument vector has in its first position the name of the process itself, right? In this case, push swap, but in general, it is a.out. It is in the position 0 of the argument vector. So here I want to put a placeholder in the argument vector position 0, because it is going to be easier for me to init the stack with this gimmick. So this is what we are going to do. And the second one is going to be a pointer to null. Basically, I have one more for the first element, which is a placeholder, and the last element, which is a null, to delimit the end of this 2D vector, right? So I need to malloc size of char per 4 in this case. Now you see it visually, it's super easy. You see, I have 4 pointers here. This time I have the stuff which is in the heap. So we have to free this stuff at the end. Otherwise, we're going to have some leaks. Okay, now I have a stupid printf. It's going to just print 32 numbers of bytes allocated. The pointer is 8 bytes. Every time you do a malloc, it's good practice to check if the malloc is returning a null pointer. This never happens, but anyway, this is good practice, because if it happens, your program will crash because you cannot reference a null pointer. Then what do I do, my friend? I have this while loop. What is doing? While words number minus minus, so I have a postfix decrement, major equals 0. Words number is equal to true, right? As you can see from here, minus minus, major equals 0. So I have 2, 1, and 0, major equals 0. So this loop is going to go on for 3 times. I say, if 0 equal to I is just this variable that I initialize to 0. It stands for iterator. The variable I is always used for as an iterator, or I, J, or K. These are usually the names, but I is the most used. I say, if I is equal to 0, you put in my vector strings, in position 0, a simple char. So I do a malloc size of char. This is the placeholder for the name of the process, right? So what do you do? Let's watch it visually. If 0 equal I, vector in position 0, I malloc of a char, then I have as usual my control, if null equal vector string I, etc. And then I say vector strings in position I with the postfix increment in position 0 is equal to 0. Watch the image. What is happening? Boom. So I have my placeholder. Okay, I have a char that stands for the program name. Then we keep going on because I have the continuum. The continuum is just a jump. The continuum is telling, okay, just go back to the while, go back to the beginning of the loop. So we jump from here to here, continue, boom, and we keep going on. This time we're going to skip this if, and we are going to do that. Next, vector string in position I++. And here I have another function which is not super simple. Get next word. Get next word that takes as an input the string and the separator again. Let's watch this function in action. Next, so as you can see, I have my function block that is allocated, and inside I have a lot of stuff. So here I have a very strange stuff. As you can see, here I have 2 times the word static, that now we're going to understand super well what it means. I have static int cursor equal 0. Let's watch first of all the animation, so it's going to be easy to understand the explanation. So we declare this variable. As you can see here, the static, which really changes the behavior of a variable. So it's really important. As you can see, get next word has access to the string with this pointer, and then we just start. The idea of get next line as the name implies, is to fetch the following string. Okay, that's the idea. Every time it's going to take a string and give that string back to the caller. So I have a variable, which is len, I, as usual for the iterator. And then I say, while str cursor equals separator, just keep going on. This time I don't do pointer arithmetic, but I'm exploiting the cursor variable to move inside the string, right? I'm not increasing str per se. So until I have a separator, just keep going on, move the cursor inside the string. So initially I have the h, so I just keep this line. Then I say, while str cursor plus len is different from separator. And of course, str cursor plus len is different from 0. This is implied. Namely, I am still inside the string. What do? You increase len. This time I use directly pointer arithmetic with len. So I increase len by 1. As you can see here, it is increasing. Keep going on. We keep going on. I have len 5, which is exactly hello, the len of this first string. Now, str plus cursor plus len is equal to the separator, right? It's pointing here. So what is happening? This while loop is going to break, and I have this call to malloc, which is malloc len per size of char, which is 1. This is redundant. I could have used also len plus 1, but anyway, this is more readable, I guess. I have a malloc. So look the get next word. I have a malloc here of 6 bytes. 6 bytes because I have to put inside this string. Of course, here I have my usual control. And I say, while str cursor is different from separator, this time I'm going to exploit the cursor variable, as you can see. And the string is not finished. What do? You just copy. This is a copy string very fast. So you just copy inside the next string in position I plus plus, I is equal to 0, is equal to str cursor plus plus. Cursor, which is 0, as you can see here. Okay, let's watch the animation. So as you can see, I have the copying. At the bottom, I'm going to append the \0, which is, of course, the sentinel value to tell that the string is finished. Okay, cool. And here, as you can see, my friend, I have the hello string that has been basically fetched from the mother string, which was in this one, right? The literal string. And basically, here at the bottom, I have return next string. Easy peasy. So this get next word is going to return this hello. Okay, next. Boom, we go back and then back to the previous function we were here. Vector strings is equal to get next word. So I have inside my array of pointers in the position I++, namely in position 1, this string, you see? Now, you have to understand one important thing here. Then we have finished with this split. When the function get next word is going to be called again, what is going to happen? Boom, we go inside the get next word. This time, look at the value of cursor. This here, cursor is 5. So cursor has been able to save the previous state. So now you perfectly well understand what is a static variable. A fairly easy way to understand the static variable is like a global variable, which is accessible only by a specific function. In this case, the get next word function. Only this function can access this value. So we can simply say that a static variable is kind of a global variable, which is private, a private global variable, I would say. And here we have to understand some other things. As you can see here, I have static, which is at the function level. Basically, I'm saying this function here, all this function, the get next word function, all this one, is static. And here, on the contrary, I'm just saying, hey, this variable is static. This static and this one are qualitatively different. When I say that a function is static, it means that it is accessible only on a specific file. On the contrary, when I say that a variable is static, like this, I'm saying, hey, just make this variable like a private global one. Basically, it has to recall its value. And here, it is very important that you initialize the variable in this fashion. This is not an assignment. This is an initialization. Because if I say cursor equals 0 at this level, just above the len equals 0, every time you access the function, this static variable is going to be refreshed to 0. So we have a difference between initialization and assignment. These are the subtleties of the C programming language, okay? There is plenty of details everywhere. As usual, I prompt you to watch this video. What is a static variable from CodeWorld? I am promoting all these videos. It seems like we have a collaboration, but no, we don't know each other. Okay, now that you understand the power of the cursor, you understand what is going on here, right? Let's watch very briefly the getNets word in action. This time, having the cursor starting to 5, I'm gonna search for the next word, right? Very simple. Then let's watch just the animation. I have the next word that is gonna be copied here with the malloc. The string is gonna be returned to the caller, and then it's gonna be linked. At the end, I have my null, which is appended here. You see? In this line, vector strings in position I equal to null, then return vector strings. Basically, the split function is finished. So here I assign to argv this structure, which is specular to the argv, right? It is an array of pointers. At the first place, I have a simple placeholder, which is like an artificial name of the process. While on the first and the second one, I have the string themselves. At the last position, I have my sentinel now. Of course, I am dealing with numbers, right, in my push swap. So here to make more realistic. 12, 34. Let's watch with some numbers. With the numbers, my friends, I get something like that, right? I get an argv only with the numbers. Of course, I recall to you that all the arguments coming from the command line are strings. So we have to convert this stuff into numbers themselves. Okay, now you basically understand what is going on with the split function. So this is not super easy, but it is necessary. So we are here, right? We are here, and I say if argument counter is equal to 2, namely I have only 2 inputs, like I just showed you. What do? You call this function ftSplit. We give as an input argument in position 1, namely the string with all the values, and as a separator, a space. Easy, right? Now you understand what is going on. Now, at this level, what do I have? I have my function stack init, stack initialization. Basically, this is the creator of the world. So it's the creator of the stack itself. And as you can see, I can just simply give as an input argument vector +1. Argument vector +1. So we start immediately from the value itself. That's why it's fairly useful to have in my split function the element which is in position 0 to be equal to a placeholder, because here I can give to the init simply argv +1. Stack init doesn't really know if this is the argument vector coming from the command line or mine artificial array of pointers. That's basically it. So now we have to understand this stack init, what is going on. As you can see, stack init is another file here that I called indeed stackinit.c. Inside this file, I have all the material, all the code to create the stack and to check for some potential mistake. So let's watch the stackinit function, which is at the bottom. So it's going to create the stack with the command line values. Checks are embedded in the creation itself. Indeed, while I am creating the stack, I'm also checking if something is not correct. As usual, this is composed of many bits. This is indeed not super simple, and we're gonna see everything with animations in CTutor, which is always the best thing. So let's watch very briefly my main function. As you can see here, I've created v. What is v? V is an array of 5 elements of what? 5 pointers. Yeah, we go to the right and left of pointer to char. So I have an array of 5 pointers to char, and then here I just initialize all the pointers basically, right, with string literals. I have \0, 42, and so forth. Basically, I'm recreating an argv. Then I call my function stack init, and I give as an input the address of A. This is important. It has to be the address. As an input, I give v +1, which is argv +1. Here is a mistake. You can basically forget about this fault. This is just to me to do some checks. All right, let's watch how this stack init works. We start as always from my main function. I have my pointer, which initially is to null, and then I have my array of pointers. Let's watch. As you can see, I've created this. I have my 4 numbers. This is the placeholder for the artificial program. And here I have my first number, my second number, and my third number. At the end I have my null sentinel. So my stack init is taking as an input this v, okay? Thinking that this is the argv, but this is just artificially made by me now. Okay, I have my argv. Argv is pointing to the first element, right? As you can see here, I have argv that is pointing to the first element that is pointing here. Argv is pointing to the first element of my array of pointers. So I skip basically the first one. And look carefully here. I have A, which is a pointer to what? A pointer to a pointer that initially is null. And this is very important because this will allow me to change the value of the pointer itself. And that's what I want. I want to change the value of the pointer, which is inside the main function. So we start. The algorithm basically what it does is say while at argv. Argv is a pointer to the pointers, right? So while I have elements inside this array, what do? We keep going on and I say number is equal to a toll. This is a function that is going to take a string as an input and give me back as an output a long. Okay, so this is a conversion between strings and numbers. Of course, this is the one coming from the library. It is not implemented by me, but in the code I made, I created my own a to long. Later you will see it. So look carefully here, a long. What is going to happen? I click next, and I get 42. Of course, this is the element pointed by this, right? 42. This string here has been converted to 42. Okay, now I have my value, which is indeed an integer. It is not anymore a string. What do I do with that? Well, I check if this is overflowing the integer max or the integer minimum, right? That's why I need a long. I need to convert the string to a long so I can check the overflow. So the number is 42, so it is not more than int max. So you skip this code. So you go here. You go if error repetition, and it takes as an input a pointer to my stack and the number itself converted to an integer. So basically, as you can understand, in my stack, there cannot be repetitions. Basically, this is illegal. 42 is not legal. Here with this, we are going to check if the number is already on my stack. Now the stack is empty, so I have this control. If null equal a, return 0. Basically, return false. There is no repetition. And we go on. So now we have seen that the number is not overflowing. It is not a repetition inside my stack. So now you append the node. Okay, you append the node with this function. Append node int number. So I have a pointer to the stack, and now I'm ready to rumble, right? Append node. What is doing this append node? Is gonna declare a pointer to a node and then a last node. Basically, is gonna create a node. Node is equal malloc size of type stack node. So it's gonna create a brand new node, as you can see from here, right? A brand new node has been created with the malloc, and it's gonna initialize with some values. For example, the next pointer is gonna be null, and the value is gonna be 42, right? Initially, namely, it's gonna be this value here. Then here I check, is the stack empty? Namely, it is equal to null. So now you understand very well why I initialized my stack to null. Well, if the stack is empty, you put as a first node a pointer to the node, right? Because node is a pointer to the node. Basically, you have to put this pointer here that is pointing in this node, where inside the main here, you have to put inside here. So pay attention here. Look at the A. I click next. Boom. Now I have the pointer A, which was previously null, in my main that is pointing in the node. You see? Cool. Let's go on. And now the function is finished. Now I have successfully changed the value of the pointer to the node, which is in the main, to the first node, which is 42 in this case. Let's go on. Let's watch another one, and then we are done. I think you understand the idea. We keep going on. We increase argv. So we convert, again, the value of the string into a number. We check for overflow. We check for repetition. We see that we don't have a repetition. So error repetition is going to return false or 0, the same. And then we call again the append node. Append node, what is going to do? He has a pointer to the first node. It's going to perform his calculation. It's going to create a brand new node, as you can see. It's going to assign the value. Next is equal to null, because every new pointer, of course, has a next null. But this time, look here. I have if null equals stack. This time, A is not equal to null, right? It has a value. So we skip this if, and we search for the last node. So we have to search for the last node of my linked list. In this case, my last node is the first one, which is 42. So we search for it. The function last node is searching, is doing its calculation. You can check, it's a very easy function. So it's returning a pointer to the first node, to this one. Okay, that's all there is. So I have a pointer to the last node. Append node has an access to the last node, and it's telling last node next is equal to node. You see here, look to the first node, what is doing. Boom, is pointing toward the next node. Okay, easy peasy. And then it's saying node previously is equal to last node. So node, this one previously, which is this value, is equal to the last node, which is this one. Look now, boom, you see? I managed to create this link within two nodes. And then we are left with what? We are left with the first node, the second node, and A that has changed, right? Thanks to the pointer I have here, I can change the value of this. And I have my linked list, which is living in the heap, memory, okay? With all the nodes. Of course, this is going to continue until I have all values here, okay? We just keep going on with the animation. And at the end, of course, what do we have? Let's remain to the main function, like that. This is the final configuration. Now, let's make in such a way that this is visible. I have my main function. Inside the main function, I have a pointer to a node, which is the first one, in this case 42, that is pointing to the next node, which is this one, which is pointing to minus 21, the last node. A linked list. Every node knows who is the previous and who is the next, and we are ready to rumble. As you can see, I have in my main function all the nodes which are in the heap with the value and with some metadata. In this case, I don't have all the data that I'm going to need with my algorithm because it is just a demo to show you how the stack init function works. What do you think? With the animation, I think it's pretty straightforward. So this is the real function. As you can see, stack init, I have if error syntax. This is another control that I skipped, but it is just to check if I have some strange values. Then I have my ft a2long. This is this function. Hopefully, it's fairly easy for you to understand. If you understand the concept that I'm explaining to you now, this a2long, it's easy vanilla. And here I have all the other controls. Basically, if I have a mistake, I have this function, which is error-free, that takes as an input a, argv, and flag argc true. Basically, this is a flag that is telling me, hey, pay attention. The argv is the one artificial that we have made. So it is in the heap. You have to free that. So if it is true, I have also to free my artificial argv. On the contrary, you just free the stack A. That you see, it is the structure here that is living all inside the heap. This is stuff which is all inside the heap that we have to free. Otherwise, we are going to have a memory leak. If all these tests are passed, we have the append node that you saw, just creating a node and appending in my linked list. And that's it. At the end, I have just, if I don't have any kind of mistake here, I have my pointer A that is pointing to the linked list ready to rumble. You can see here, right? In my main, I have a pointer to my linked list. And then I have just to discard my metrics that I have created in case I have two arguments, as I just told you. So I have an helper file for this stack init file, which is stack utils. Stack utils is this file that contains a lot of functions that are useful for the creation of the stack. For example, find last node, fairly simple if you understand the linked list. Append node, which is the function that you just saw, that is attaching a new node. Then I have a function that is finding the smallest node, but this is stuff for the algorithm itself. Then I have a stack len. You will see later. Basically, stack init, stack utils is stuff that is working with the stack for creation or for finding some information that is going to be useful for my algorithm. Okay, we finished with the stack init. So now we are here. You understand what is going on. At this point, we are here. We have a pointer to all this data, to all these nodes. And now we have to implement the commands that we have to perform on our stack. As I told you, we have a set of commands that we can use. So this is our constraint. We can sort the numbers inside my stack only with specific commands. Then now I will show you. Basically, here is still part of the stack implementation. So here we are in a phase in which we have to add some functionality to our stack. We have to allow our nodes to move around. Especially we have to perform the swap, the rotate, reverse rotate, and push command. Let's watch it visually, so it's going to be easy vanilla. So I have my stack. Now you understand you have a pointer to a node that is pointing to another node, that is pointing to another node. These are the arguments coming from the command line, right? We have made all our checks. We know that we don't have any doubles, that we don't have doubles, meaning repetitions, and we don't have any strange symbols and so forth. These are full-fledged numbers we can work with these nodes. So how to perform the swap? Just look carefully what is happening now with the stack. I perform the swap. Basically, I have the second node that is going in the first position. It is a swap. So I have the top node that is going in the second position. I think it's easy, right? You have top node that is going in the second position. Easy peasy. So you swap the top two nodes like that. Then we have another command that is the rotate command. Basically, the rotate is like taking the top node and bringing it to the bottom, shifting the ones which are just above. Let's watch the visualization. So 42 is going to the bottom and the other two are shifting upwards. Easy peasy. Then we have the reverse rotate command. What is happening? Well, it is happening the opposite, basically. We have the bottom node that is going to the top position and the other two are shifting down. So we have this operation here. And then we have the push operation, which is the operation of pushing, namely taking the top node and adding to the top of the other stack. It's like taking a plate from a pile of plates and putting to another pile of plates. It's like that. So watch the animation. You have something like that. This is the push operation. Top node in stack A is going to top node in stack B. Push. So these are the operations that we have to implement in code. This is the functionality that we can access to sort our stack. Okay, this is the constraint. This is the difficulty of the exercise. For example, if you have only to sort two nodes, what do? Well, you search, is the first one the biggest? If it is, you just swap and sort it. So the commands, thanks to the data structure that we decided to use, basically a linked list, it's fairly easy to understand. We just plug and unplug some pointers, as you can expect. So here, as you can see, I have some files. I have reverse rotate command. I have the rotate command, the swap command, and the push command. Basically, I have 4 files that are implementing this functionality to my code. Sorry, this is not the push command. This is the push command. Here we are. So they are fairly small files, 50 lines of code each, but less. The code itself to swap, for example, is 9 lines long, no less, 8. This is the lines of code to swap 2 nodes in a linked list. Maybe the push is longer than all the others, but still, it's like 20 lines of code. The rotate command, look at that, is 1, 2, 3, 4, 5, 6 lines of code. 6 lines, you just plug and unplug the pointers and it's done. It's not terribly complicated, and at the end, it's elegant, in my opinion. So again, we're going to have a visual understanding of what is going on. So this is just a demo program to show you the commands. In this case, I'm going to use the rotate a command. Let's just check the output. I'm just going to compile, and then I'm going to launch. As you can see, I start with some nodes. I have the value -4, 8, and 9. Then I perform the rotate command. So basically what is happening in the rotate, top goes to the bottom and the other two are shifting. As you can see now at the bottom, I have -4, 9, and 8. You see as well, rotate. And then what do I have? I have 8, which is at the bottom, and the other two are shifting. So every time I get this rotation and all the pointers are changing, as you can see. The previous now is 0 because it's pointing to the head of the stack. The next is 4, 9, 8, and so forth. I think you understand what is going on. Every command is gonna perform some manipulation of pointers, and that's all there is. So again, we're gonna exploit our visual tool. So what do? I create artificially linked list in my main. So here it comes. I have my linked list, as you can see. A is pointing to the first node, that is pointing to the second, that is pointing to the third. Marbles. Now I call my function push. So basically I want to take the element which is at the top of my stack, in this case 42, goes as the first element of B, right? So I have a pointer that is pointing to B. So basically I just search for the node to push, which is equal to the node pointed by A, right? So it is this one, the first one, because in the push I take the top element and I put on the other stack. So I say, okay, now the pointer A is pointing to the second one because I remove that node and I put on the other one, as I just told you. So look carefully now to pointer A, boom, it's pointing to the second node. So basically I've changed the stack thanks to this simple command. Then I say the previously of this node is equal to null. It is not anymore this node, right? You see? So check it out, this command here, boom. Now this pointer as a previously, which is equal to null. That's exactly what I want because it is pointing to the head. So basically it's null. Then we keep going on. Here, the big leap is that I put inside dest the node to push. You see here in my main, now it's pointing to null, but now it's gonna point to this node. Boom. So now I have B that is pointing to 42. And then I need to change the next, right? It's not pointing toward anything now. So look carefully now, not to push next equal null. So I've managed to detach this node from A, and now it's only on B. Okay, this is the push operation with the pointers. Easy peasy, right? Now A is pointing here, and B is pointing to this node. As you can see, 42, which was at the top initially, is now only on B. So we started from here. You know that in the push, I would like to take the top and put on the other stack. And with this pointer dealing with these simple operations, we managed to reach this final combination, which is what we want. Okay, you easily understand that all the operations are like that. Here, for example, if I do rotate, that's the same idea, right? Now I have just to change. I just have to remove this and add one, because rotate, of course, is acting only on one stack. So what is happening here? Basically, it's the same game. I just change a little bit. I create my linked list in my main. Then I call the function rotate. Rotating, what is doing? Has access to the pointer pointing to the first node. So with that, I can basically change the value. Now we understand super well, I'm sure. Then what do? You find the last node. So you have a function that is finding the last node, which is this one. Boom, it's pointing there. So it's returning this pointer. So thank you, find the last node. Now I know where is the last node. And then I say, okay, in the rotate, I want the first node to be at the last. So A has to point here, and I have to change a little bit the pointer configuration. So now you can check by yourself what is going on with this. I won't explain line by line, otherwise it's going to become super cumbersome. Just watching the animation, you understand what is going on, right? You get the pointer out that is pointing toward 1337 minus 21 and then 42. So you see, we managed to implement the rotation of our linked list. We started from 42, 1337 minus 21, and we want to finish with 42 at the bottom and this at the top. And indeed, this is what happens after the algorithm, as you can see, right? This is the same idea for all the commands that I have implemented with my files. So it is just a deal of plugging and unplugging. I repeat again to you, just understand by yourself what is going on. Just check very carefully all this plugging and unplugging. It can be a little difficult if you feel not comfortable with linked list. Indeed, it is kind of cryptic, but once you get used to it, it's not terribly difficult. And you have the plus that it's fairly easy to implement this stuff. If, for example, if you have an array, well, you can do as well. I mean, it's up to you, my friend. Your code, your decisions. Remember that code is just an extension of your thoughts, and you just have to crystallize your ideas about a solution. To me, it's elegant in this fashion. I highly suggest to you to watch this video from CS50, amazing data structure, which is really giving you the idea of this linked list plugging and unplugging with physical objects, which is what is going on essentially in our code now. So now we have managed super well to implement the swap, to implement the rotates, to implement the reverse rotate, and to implement the push thanks to an auxiliary stack, which is stack B. Okay, so data structure done, commands done. Now it's time for the algorithm. How we implement the algorithm with this data structure and with this functionality that we have access to. So here I'm just gonna generate 500 numbers. I'm gonna copy all of them, and I'm just gonna launch my program, push swap, with all these numbers. Launch. And as you can see, this is the idea. These are all the operations to perform to sort my my numbers, with the constraint of using all these instructions. So now let's understand very well the algorithms that I'm gonna use. First of all, I have a tiny sort. So in my project, I have a tiny sort file in which I have all the stuff that I need to perform this tiny sort. What is the idea of tiny sort? Well, it's the idea that if I have only 3 nodes, it's gonna be super trivial to sort these elements. Let me explain you why. First of all, you see the code, which is this one. Basically, it's these 3 lines. So 3 nodes are trivial to sort, super trivial. Why? Let's understand very well. The first question I make is this one, namely the first one, the biggest of the 3? Yes, in this case it is. So what do? I just bring it to the bottom like that. I just say, okay, you go to the bottom. I can do that because I have the rotate A command. Rotate A takes the one to the top and brings to the bottom. Easy peasy. Next step, I'm going to say, I know the biggest one is at the bottom. Who is the bigger between first and two? Well, in this case, this is the first one, 42. So what do? I perform a swap. I swap the two. You see? As you can see now, I have the three elements which are swapped. So the tiny sort algorithm basically implies make sure that the biggest is at the bottom and swap the first two nodes if needed. Now let's understand this idea in code. Here I have a node which is the highest node, which is basically is the highest node, the one which is the biggest, the highest, right? The highest value. And I say, is the first node the highest? Well, if it is, rotate it, like you just saw in the animation, right? On the contrary, if it is the second one, the biggest, what do? You perform a reverse rotate. So you take the one at the bottom and you bring to the top. So basically you achieved the same goal. You have bottomed the biggest. If this is not the case, and this is not the case, what does it imply, my friend? Well, it implies that at the bottom I have the biggest already. So I don't care anymore about the biggest with these two instructions. You see? The only thing I have to care is if the first one is major than the second one. If this is the case, you perform a swap. So this is a tiny sort. To sort 3 nodes, it's super trivial. Let's perform again a test with 3 nodes. We're gonna perform only 10 tests. Okay, so we're gonna see how many instructions we need with 3 nodes. As you can see, I have an upper bound. I have an upper bound of 2. Mathematically speaking, this is not get bigger than that. Maximum is 2 operations. Worst case scenario. Thanks to this little argument. So I handle 3 elements in this fashion. Easy. Now, the problem, of course, the real core of the algorithm is to sort a series of numbers which is bigger than 3 nodes. Like in this case, I have 5 nodes, but as you saw, I can have multiple nodes. I can have 100, 500 nodes. What do you do in this case, given that you have only those operations? You have swap, rotate, reverse rotate, and push. What do? Well, you have to work out an algorithm. And now I'm going to show you the algorithm that I thought for this specific. Of course, we're going to need the stack B in this case. We just cannot do our magic only with stack A like when we had only 3 nodes. So what do? I say, okay, I know that to sort 3 elements, it's like my base case. When I have 3 elements in my stack, I perform tiny sort. This is my base case. I can do it very easily with no problems. So I push all the elements in B until only 3 elements, 3 nodes remain in A. Okay, so I do that. Once I get this situation, is like my base case, I repeat to you, and I perform my tiny sort to the stack A. Okay, so tiny sort, my stack A with maximum 2 operation is sorted. Now, what do? We have to perform a precise insertion of the node from B to A. And this, of course, is the difficult part because we have to engineer a strategy. So what do? I decided that every node in B gets a so-called target node. And what is this target node? What do I mean by that? Well, the target node, as you can see, is a node which is bigger than the node in B. In this case, I'm using 42 as an example, but not only bigger. It has to be the smallest bigger. This is kind of tricky to understand, but give me some time. On the contrary, 1337 gets minus 21. This time is not bigger because 1337 is the biggest. So I cannot find something which is bigger in stack A. So I search for the smallest. That's the trick. Now, probably it is the best option to explain this this point with a real case when I have many nodes. Now, look carefully here. Every node in B has to be mapped with a node in A, right? So every node has to get a target node that is bigger, as I just told you, but at the same time has to be the best fit for the current state. So, for example, minus 48 would like to take as a target something which is bigger, but has to be the smallest bigger. So what is in this case? I have minus 21, minus 16, and 96. The smallest bigger is minus 21, right? So minus 48 is getting minus 21. Why? Well, because I want to push this node just above minus 21, respecting the ascending order, right? So if I put minus 48 just above minus 21, I have the ascending property. Easy peasy. Minus 3, well, it's getting something which is bigger. Well, minus 3 is getting 96, is the only one which is bigger. 100, there is nothing bigger than 100 in the stack A, right? So what do I do in this case? In this case, I want the smallest. I want the smallest, which is minus 21. Why the smallest? Well, because you have to think that this is like a round object, right? This linked list is like a ring, basically. I can rotate. So I have the biggest, which can easily be just above the smallest. At the end of the algorithm, I just rotate until I have my linked list, which is in order. So I have 100 that is pointing to 21, and then basically all the nodes are gonna just be mapped to a specific node. Okay, now I have all the nodes that have a specific target node, which has to be the smallest bigger. If I don't find anything which satisfies this condition, the target node is going to be the smallest because these are round objects. Easy. Okay, my friend. Now, this is the code. This is the code to set the target node. As you can see, if you watch only the code, it's not super simple, but if you understand the principle, not terribly difficult. I have a while B, namely until I have elements inside my B linked list. What do? You just iteratively search for all the nodes which are in stack A and look carefully about the condition that I highlighted. If current A value is major than B value, namely if the node has a value which is major and at the same time is the best fit, at the same time it is the best fit because it has a value which is minor that best match index, which is going to start from long max. It is a simple placeholder. What do? You set that as a target node. So you look for all the nodes inside the stack A and you search for the best fit. If long max is not changed, it means that I haven't found something which is bigger. So you find the smallest. That's the idea. I think if you watch the code and with the explanation and with the visualization, it's not super difficult, right, my friend? I think nothing terribly difficult. Now that I have all my target nodes, I have to decide what move to do. Who shall I move now? I know that 3, for example, is just to go just above the 96. And now another trick. I have to assign to every node their current position. Now, my friend, you understand super well this current position value here, right? Every time a node has a specific position, depending of the specific configuration of the stacks. So given this current position that every time has to be refreshed, this is dynamic, as you clearly understand. Every time you make a push, everything is going to change. I can exploit these positions to get a push value, a push price. What is this push price? Well, this push price is the sum of the current position of the node and the target node. For example, let's take -3. -3 has a current position of 0 and 96 has a current position of 2. But this is not totally correct. Why? What does it mean that we have to add the positions? Well, I can perform the push with the top elements, right? So the cost is how much does it cost to bring the element and the target element to the top position of the stacks? Namely, how much is the cost to bring -3 and 96 at the top? As you can see, it is not 2, right? The cost here is 1 because -3 is already at the top position, while 96 is at the bottom position. I just need to do a reverse rotate A, right? I just have to bring 96 to the top that I can do with one move. So the cost is not 2. What can we do? We can just perform a subdivision into parts. I have a upper median and a below median, right? With this view, I have only the elements which are in the middle of the stacks, which are the most expensive, as you can see from the image. It's fairly simple. So the cost is proportional to the position and the length of the stack. The first half is easy, is the position itself. After the median, that is just length divided by 2, what do you get? You get the cost, that is the length minus the position. For example, 96, the cost of topping it is equal to length, which is 3, minus what? Minus 2, which is the current position of the node. So I get 1. This is the cost of topping 96. Just look at the slide. It's fairly simple to understand this idea. So I get a total cost that I call push price. Push price, as you can see, is this value here. Now you can understand even better this Boolean above median, and you can also understand why I have this cheapest. This final index I used for an optimization. Now I need to cancel it because I'm not using anymore. So just pretend there is not. You have a current position, a value, push price, above median, and cheapest. Then you have a target node that you understand, a next, and a previous. So you have this node that is carrying out all this information. Easy. So here, every time we have a set price routine that is setting the price to all the nodes given the current state. So it's going to say, okay, -3 is going to cost me to push 1 because I have to rotate 96. And then I don't consider the cost of pushing from B to A. I just exclude the push cost. It's the same, right? Then I say -48. What is the cost? Well, it is, again, 1. 100. This time, what is the cost? It's 2. 9 is 3 plus 1 is 4. You see, every time you get a different cost given the specific state. This is a fluid stuff. It always changes. I think you understand super well. So every time you have to refresh the position, you have to refresh the target node. You have to do all the time for every push operation. So I found the cheapest. Which is 1. You have, of course, many ones that have a cost 1, but you choose the first one. That's logic. So this is the cheapest, which is the one with the value -3, and its target, which is 96, which is the smallest bigger. And then you just need to top these nodes, right? One is already topped. The other one, you just need to perform the operation, reverse rotate A. Cool. Now I have these 2 nodes which are topped. And now what do? Well, you just push, my friend, right? Push. And we are done. You see, now I have another configuration. I have to refresh all the position, all the prices, all the target nodes, and so forth. But this is the idea of the algorithm. Every time, find the cheapest and perform the push B. So let's go to this file. This file is called push swap command. And as you can see, I have my function. We're going to just understand the principles here because you have a clear understanding of what you have to do. It is just the code that is implementing what I just told you. So here I just have a special case to handle when we have 5 elements. So I want a better algorithm for 3 and 5 elements. I have tiny sort, and for 5 I have another algorithm that is handle 5, but nonetheless is not a key moment. Then what do? Else, if len is not equal to 5, you just put everything as I told you in B. So you just push everything in B until you just have 3 elements in A. Then you perform the tiny sort on A, and then you say, while at B, until you still have nodes in B, what do? You init nodes. If you recall before, I just told you that every time you have to refresh the positions, the target nodes, and so forth. Well, these init nodes is going to perform exactly the task. So I have a file, which is pushswap init, that is performing all of that. Is setting the current position, setting the target node, setting the price, setting the cheapest. We are going to very fast watch what is going on. Set current position is super simple, right, my friend? You just have an iterator and you just give the value of I to the specific node. And in the way of doing that, you just say, okay, this is just above the median or under the median. You see? Easy. Set target node is the algorithm that is gonna decide which is the best fit for the specific node. Basically, is this function here is deciding, okay, this is the best fit, namely this is bigger and this is the smallest bigger. Otherwise, I'm gonna set the best solution as the smallest one. Thanks to this, I will have finally stack which is in order, in ascending order. So target node is this one. Then I have the set price. Set price you saw before is just basically adding the position and the relative position depending on of the median, and you understand the stuff, right? You understand. Is the price of moving node and target node to the top. Every time I want to top, what is the cost of topping node and target node? This is the push cost. So you set the price with this, and then you set the cheapest. Easy. You just flag, okay, this is the cheapest, and that's it. It is a flag inside the node itself. As you can see, at the end, you have best match node, cheapest equal true. So you just flag, okay, this is the cheapest node for this specific iteration configuration. So we are here, right? While B, init nodes. So every time you init the nodes and you move the nodes. Init node, move node. Init node, move node. This is the algorithm, basically. This is the push swap, as I understand. Now we have to understand these move nodes, which is not super easy, but now we try to understand it better. So move nodes is this one. What do? I get the cheapest. So every time in every configuration, I have one cheapest. You understood that. This function is going to return me back a pointer to the cheapest. Now I know that you are the cheapest. I want to move you. And then I say, if cheapest node, so if this node is above the median and the cheapest node, target node, is above the median, what do? If both cheapest and target. Like in our case, -3 and 96 are not in the same half, right? One is the upper half and the other one is the lower half. As I coded the algorithm, you can optimize here, I guess. So in this case, this Boolean expression that we just saw is false. But for example, for -48 and -21, they are both in the upper median. So in the case they are both in the upper median, you rotate both. Okay, this is a special function that now we'll see, but you understand, right? You can perform rotations simultaneously, and this will halve the cost of the moves, right? If you can do 2 moves simultaneously, it's like halving the cost. On the contrary, if they are both in the bottom half, what do? You reverse rotate both, and then you have 2 calls to finish rotation. So let's understand the rotate both and reverse rotate both. So I have my pointers to stack A and pointers to stack B. Of course, you know that a pointer to a pointer because I have to change the stack A value, okay? And the cheapest node. And I say until at A is different from the cheapest node, target node, because in A I have the target nodes. And at B is different from cheapest node. What do? You perform reverse rotate. R stands for reverse rotate. They're rotating both, okay? So when I have the condition and one of the two is true, this is gonna become false, but I have not topped both, right? I still have to do something because maybe I reached the target node in A, but in B, I still haven't reached the cheapest node. This is like rotating simultaneously, okay? Nothing super difficult. Then, of course, I refresh the positions because the positions have changed, as you clearly understand. So I want to exit the function with the refreshed position. And as you can see, at the end, I have finish rotation B, finish rotation A. I repeat, finish rotation is a function that is gonna need the rotation of A or B. So it's gonna say, are we finished with the rotation of the stack? Namely, is the target node in A or the cheapest node in B at the top? If it is not the case, just finish the rotation. And here there is a little of optimization. Basically, I'm telling if the top node, in this case, top node can be the target node or can be the cheapest node, because here I call the finish rotation with the cheapest node and the cheapest target node. So the function itself doesn't really know what node is moving. And as you can see here, I have a char stack name every time I have the name of the stack I'm using. So the function knows what to do. Here I can call RA and RB and so forth. So I check if this node is above the median, you rotate it or reverse rotate. That's why here all the time I refresh the current position. Okay, so this is gonna finish the rotation. I have the true elements at the top. So the last move nodes function is push A. Basically, take the element from B and put to A. Push A. Easy. Finished. So every time I have this algorithm until I have elements in B. So this is gonna continue until there is a node in B. At the end of the day, when I have the last push, B is gonna point to null. So this is gonna become false. So my push swap in 2 lines in its nodes every time just give the value of the position of the target node, the price, and so forth, and move the node. That's it. Then I have one final optimization, which is set the current position of A. So every element now in A is basically sorted, but I don't have the smallest at the top. It is sorted, but maybe the smallest is at the medium of the stack and so forth. So I have to search for the smallest node. And I say, if the smallest is above median, so if the smallest is above the median, indeed, what do? Well, you rotate it. You perform rotation. So you take the top node and you bring to the bottom. On the contrary, you do the opposite. So I think it's pretty easy. You understand masterfully what is going on here. And that's it, my friend. That's the push swap. Of course, I will push this baby into GitHub so you can dig us down as you want. This is not perfect. I think there's something that I'll still have to check, but it works. Of course, would be marvelous if you in the comments suggest some more optimizations, and if you can tell me, hey, there you suck, you didn't do exactly, you can perform it better, or so forth. So I hope you derive some value from this, and yeah, I explained as the best as I can. Of course, I cannot stop to every line, otherwise we stay here all day long, all nights, and 24 hours to make one video. All right, that's it, my friend. Thank you for watching.